record. There we go. Whoa. That's an interesting new feature of the phone. And where is he? He's not on there. Oh man, the one day I need, well, hopefully he'll come in. Oh yeah, so let me hand these back. And let him circulate the room and then make sure the remnants come up to me. And make sure you look and see if you've got two in there. Okay, so today we're going to talk about, I just realized I put in the topic for today at the last minute, so I'm sorry. But we're going to talk about the perfect Sturm. That is, we're going to uncover this sort of unifying idea between these polynomial bases in Hilbert space through what's called the Sturm-Liouville scheme. So first of all, let's revisit the results that we've seen for at least 3 examples. 2 examples I did in class, and 1 you're doing in your homework, which hopefully you've already taken a crack at it. But if you recall, one of the ways of defining the polynomials is actually just giving the differential equation that they satisfy and then stating these differential equations are the solutions to these, or sorry, these polynomials are the solutions to these differential equations. It's just another way to phrase it. That's not the way that we started out deriving each of these, but it's certainly valid. Where, of course, the first expression gives us which type of polynomial? Any takers, Scott?
Nope.
No?
0?
No, what are the PNs? What do we call them? They're what? No, they have a name associated with them. You got a friend. Say it again? Yeah, these are the Legendre polynomials. The HNs are these, Scott? Hermite polynomials, and the LNs are the Laguerre. Yes, thank you. All right, you got all those given out. Cool, thanks. I know. Okay, so recall that each of these were accompanied by different intervals. And I am, for the moment, going to write the interval with infinity with the curved bracket to remind you that you don't actually include the point at infinity. But that's not an inner product. This is the inner product.
Question when you're ready.
I'm never ready.
Right, me too.
So go ahead and ask the question.
Okay. For the Hermite section,
Yes.
there's a 2n. Is that intentional?
Oh, it's highly possible that I miswrote something. That's 2n?
Yeah.
2n? Yeah?
It's supposed to be that way?
Yeah.
Cool.
Yeah.
Okay.
Wow, we've got so many people on there. Goodness. Okay. All right, now, what I want to do is I want to sort of unify this, because this looks a little bit different for now. So the very first unification we can do.
Alex, can I ask you a question?
Sure. Yeah.
So we know that for a differential equation to be well posed.
Hold on. Bohana.
Hello?
You're going to want to mute yourself. I hear the applause coming through the speaker.
Oh, I'm sorry.
No, it's okay. Okay, carry on.
So for a differential equation to be well posed, we need like boundary conditions or initial conditions. Where are those here?
So we have the square integrability condition on each function, f and g. And then there is a bit of arbitrariness in the solutions because you can rescale all of the solutions. So I'm guessing that that would provide sufficient boundary conditions for a second order diffie-Q. Is that the functions, yeah, I mean, square integrability as providing a boundary condition isn't 100% obvious, but I believe it would. And then the arbitrariness and the scaling, yeah, should pick up the other degree of freedom. Okay, so the first thing we can do is we can promote all of these intervals to the interval from minus infinity to infinity. Okay? Basically, by redefining the weight W that is used in the inner product. Okay? So for example, for the first case, we have to do nothing because the interval is already from, oh, sorry. No, sorry. Why am I writing this like this? Oh, yeah. So we have to do nothing to the Hermite. No, hold on. Yeah, the Hermite. The Hermite is already defined on minus infinity to infinity. So for the Hermite, we have that the weight is obviously e to the minus x squared, nothing weird there. For the Laguerre, okay, the Laguerre is defined on this semi-infinite interval. We would like to extend that to the fully infinite interval. And of course, one way to do that is just to throw a heavy side at it. So we can say that the weight function is hx e to the minus x, where you should all be familiar with the heaviside function. It's 0 for any value of x less than 0, and it's 1 for any value of x greater than 0. It's a step function, but all it's doing is it's saying, I want to set everything with x less than 0 to 0. And then what that means is I can take functions f and g, and I can now use this integral, but I can extend the lower bound to minus infinity. And the weight in there, sorry, I shouldn't be doing this one. I should be doing, I should be doing this one. Okay? The weight in there is actually just eradicating all contributions to this integral from x less than 0. So what you get from doing this is the same thing you get from doing this, as long as your weight function is defined with the heaviside function. Okay? And then Legendre, we can use the boxcar. How many of you have heard of the boxcar?
Just a 0.
Yeah, it's just a combination of heavisides. Okay? So for the boxcar, you actually have something like this. Where it's 0, and then it's non-zero from minus 1 to plus 1, and then it goes back to 0 again. Okay? Now, of course, for the Legendre, I don't know why I'm doing these in this order here when they're in different orders here, but I'm just being silly. But at any rate, but otherwise, the weight in the Legendre inner product is just 1. Okay, it's just 0 when you're outside of the minus 1 to 1 range. Okay, so we know we can generalize the intervals to be a common minus infinity to infinity. Now, let's take the equations themselves and see what sort of general framework we can extract. So first of all, notice that all of these can be written in this form. Because in each of them, I can take the last term and move it to the other side of the equal sign. And then I've got something which is doing a second derivative and multiplying it something, doing a first derivative on the polynomial, multiplying it by something, and that's equal to something times the polynomial. That's an eigenvalue equation.
Can you say that whole thing again?
So if I take this polynomial right here, or sorry, this differential equation, the first one, and I write it like this, this is obviously an eigenvalue equation, where this is the eigenvalue. And this is the operator, which is acting on this. And you can do that with all three of them. So what we can say in general is that all of these are eigenvector eigenvalue equations. And moreover, we can write the operator L that's acting on them as alpha x d squared dx squared plus beta x d by dx plus gamma x, okay? And lambda is, of course, a constant in each of these cases. N times n plus 1, 2, n, or n, okay? Now, in all of this, you pick an n, and then you go through and solve the equation. So remember what we're getting when we're picking n? We're getting the degree of the polynomial if you're going to focus on polynomials. I'm not yet focusing on polynomials. But n is just a label, okay? But given a value of n, these are constants. So the eigenvalues are constants, all right? And notice everything has a second derivative and a first derivative. Okay, so this is sort of the generic form where the coefficients in here can be functions of x in general. Now, are you ready? What kind of operator do you think L is? Max. Is Max here? Max is not here. Lucas.
Yes.
What kind of operator do you think L is? If you had to guess of what is the most valuable type of operator that we have encountered in this entire class, what type do you think it is?
Hermitian.
Excellent, excellent. Yes, it is Hermitian. Okay? So it turns out that in all of these cases, L, the operator that's acting on the left-hand side of the eigenvalue equation, is a Hermitian operator. So let's actually go through this in detail, sort of proving it. So, she's got me tight. Okay. So first of all, recall that our definition of hermiticity is that if I'm doing the inner product of L acting on F, inner product it with G, then that has to be the same as the inner product of F with L acting on G instead, okay? With the matrix representation, you're used to the idea that this is daggered, if this is not daggered, but if it's Hermitian, L is equal to L dagger, okay? And that's a useful remembrance in terms of the matrix language, but this is the more functional language. This is the way to define hermiticity. It doesn't matter which of the elements that you're doing the inner product of, you can apply the operator to either of them and you get the same thing. Now, we of course have two expressions that involve this. The first is if I have L act on F, and if I have L act on F, that is of course L F star G dx. From minus infinity to infinity, where now I'm just going to go over this interval for everything. And this has to be equal to the integral from minus infinity to infinity of F star LG dx. Okay? And now for the operator L to be Hermitian, I need this equal to this, which means I can subtract them and set the difference to 0. So let's do that. The first thing I'm going to do is I'm going to rewrite this guy right here a little bit. So I'm going to say that the right-hand side is the integral from minus infinity to infinity of F star. And now what I'm going to do is in place of L, I'm going to put this more general expression. Okay? So we're going to have alpha G double prime plus beta G prime plus gamma G. Okay? We remember, I'm not going to keep writing this, but alpha, beta, and gamma right now could be functions of x. Okay? And then the weight dx. Oh, sorry, I left the weights out of here. I need to have weights in my inner products. Okay? And now we can do a little bit of rewriting. So what we're going to do is we're going to integrate this by parts, and we're going to get the following expression, f star alpha g prime omega, or w, sorry. My omegas look a hell of a lot like w's, and so I'll just interchange my verbiage. Good Lord. I know. Okay. And the left-hand side is the same. We're just interchanging f star with g everywhere in this expression. Okay? Now remember I said that we want the left-hand side minus the right-hand side equal to 0, because the left side's got to be equal to the right-hand side. So if I do a difference, it turns out that this term, and this term trivially cancel. Okay? With these two, it should be obvious. Okay, because if I write the term down with f star and g swapped, well, it's the same damn term. This one is a little less obvious, but nonetheless, these will cancel. So the content of this difference is going to be this term, minus their versions with f star and g interchanged. So if we write that down, what we're going to find is the following. Let me see. I'll do it. I will do it. I'll do it somewhere. I'll go up here. Yes, I'll go up here. Okay, so we write down what we get when we interchange those and subtract them. We're going to get W alpha times F star G prime minus F star prime G, evaluated at minus infinity, infinity, minus the integral from minus infinity to infinity of W alpha primed minus W beta times F star G prime minus G times F star prime dx equals 0. Okay? Why I wrote that so far to the right that I had to cross the line is beyond me. If it were good old OneNote, I would just do the select all, shift over thing, but we just can't do that because I'm writing for real. But anyway, I know. Okay. So, in order for this thing to be Hermitian, that is, satisfy this property right here, that difference has to be 0. Okay? The first thing we can observe is that the functions f and g are arbitrary. I mean, they have to be elements of Hilbert space, so they've got to be square integrable, but that doesn't say too much. So in general, this thing right here is not 0. Okay? So what that leaves us with, of course, is the idea that this is equal to 0 and that this is equal to 0. Okay? Now for this guy to be 0, now notice these functions they're being integrated over, and in general, the contribution to the integral is non-zero. Here, though, they're being evaluated at infinity. So you could say, I want to focus on a set of special functions which vanish at infinity, in which case this itself might cause this term to be zero. Okay? And there are some important examples of that. However, we are going to turn to polynomials specifically, and when you're working with polynomials, there's no way that's going to work. Okay? Unless, of course, they're all even. Okay? So generally, to get the first term to work out, we're going to demand that W alpha goes to 0 fast enough. That is, if you're dealing with polynomials that might grow, then you need W alpha to go to 0 faster. Okay? Here, what this of course means is that W alpha prime is equal to beta over alpha W alpha. Isn't that obvious?
Why is that obvious? Where did that beta come from?
Right there.
Oh, there. Oh. Well, yeah,
If this is 0, then W alpha quantity primed is equal to W beta, and I just rewrote it like this, multiplying by alpha over alpha. Okay, glorious 1. But the reason I did that is because now you can integrate this to get a simple expression for W alpha. It's going to be some constant C times e to the integral beta over alpha dx. Okay? Where W, the weight function, is always taken to be positive. This, of course, is an exponential, so this is always positive. So if we take alpha to be positive, alpha is the function of x that precedes the second derivative. If alpha is positive, then c is positive. Okay? If alpha is negative, c is negative. So we can just pick one convention and stick with it, and we'll go with positive. Okay? All right. Now, let me see. So now what I want to do is I want to put in the property of hermiticity. I'm going to regret erasing these, but oh well. So we're going to add the property of hermiticity to this expression, and we find the following. Yeah. Okay. LU alpha u double prime plus beta u prime plus gamma u equals lambda u. This can be rewritten, if you're acknowledging that L is Hermitian, as d by dx w alpha du dx plus gamma minus lambda w u equals 0. Okay? And then with the condition that W alpha S star G prime minus F star prime G evaluated from minus infinity to infinity equals 0 defines a Sturm-Liouville system. Okay? Now, I want you to recall a result that we derived in the finite dimensional vector space, and that is Bohanna.
Hello.
Hi. Bohanna, can you remind me what we can say about the eigenvectors associated to distinct eigenvalues if the operator in question is normal in the finite dimensional case.
They're going to be orthogonal?
Yes, they're going to be orthogonal. Good. So the question one might ask is, does that naturally extend to the infinite dimensional case? Okay. And at least within the Sturm-Liouville context, it will. So let me demonstrate as much. So here we go. We're going to take two eigenvalues, lambda m and lambda n, with m not equal to n. Then this expression can be written in the following form: d by dx, w alpha, du m dx, plus gamma minus lambda m, w u m equals 0. And then for the expression associated with dn, we can just complex conjugate the entire thing. But that's actually going to only impact the un, because everything else in here is real. Okay. In truth, I mean, I wrote down these operators and these unknown functions, and I'm assuming everything here is real. The only thing in this expression that you might worry about is the eigenvalue itself, but L is a Hermitian operator, so its eigenvalues are? Real, exactly, okay? So we can complex conjugate them if we want, but it's the same thing, all right? And then what we can do is we can take this expression, multiply it by un star, and take this expression and multiply it by um, and then take the difference. And our difference is going to end up giving us the following. Well, first of all, what's the difference between this minus this?
0.
0, because it's 0 minus 0. That's excellent. All right, so here we go. I know. So we're going to have un star d by dx, w alpha, du m dx, minus lambda m w un star um, minus um d by dx, w alpha, dun star, plus lambda m w un star um equals 0. Okay? And then we can rewrite this gently in the following form: d by dx of un star w alpha dum dx minus w alpha dun star dx equals minus lambda n minus lambda m w un star um. And then what we can do is we can just integrate both sides from minus infinity to infinity. Of course, if I integrate the left-hand side, that's going to be pretty trivial because it's already a derivative. So if I integrate the left-hand side of this from minus infinity to infinity, it's just going to be that bad boy evaluated at minus infinity and infinity. I just erase the derivative, and that's the consequence of the integral. These are constants, so I've got this. Okay? But this, of course, is un um. Now, this should look familiar. If I factor out the w alpha, wow, that's a crazy star. Un um prime minus un star prime minus infinity to infinity. What is this equal to? 0. So the right-hand side of this has to be 0. If lambda n is different than lambda m, then what is the value of the inner product of un with um? It's 0. Okay?
What did we just show?
We just showed that we just showed that eigenvectors belonging to distinct eigenvalues, that is, two eigenvalues which have different values, the eigenvectors associated with them are necessarily orthogonal. We've proven that for the finite dimensional case. We just proved it for the infinite dimensional case. Okay? You're welcome. You're welcome. Okay. Now, everything that I have said thus far has actually held. Oh, yeah, go ahead.
So I don't see how you went from this step, which is right here, right here. Because it looks like you just swept these in. I mean, I think I'm just missing something.
So my guess is this is a rewrite where if you use the product rule, you're going to end up with this plus terms canceling.
Oh, you're right, because the inner terms cancel if you take this one and that one.
Yes.
Okay,
Yes.
thank you.
Yeah, that's me sparing you some of the lines of derivation, and then you ask a question like that. I'm like, shit. I wish I had it all written down in the notes, even if I'm not going to paste it on the board. Okay. Now, believe it or not, everything that I've talked about so far is a more general definition. So these are Sturm-Liouville systems. But what we want to do now is we want to take it and we want to focus on polynomials, because there's going to be a certain story that plays out for polynomials, which is going to incorporate everything that we've seen so far, but it'll also give us some more general results. So, specializing now to polynomials, we have the following. All right. So first of all, we're going to write our expression as, let's see, I'll keep that up there. LQN is equal to lambda n QN, okay? With L the same operation as we have up there. Well, actually, no, I won't write it. It's the same operation on U up there, but now it's acting on Q. And of course, we know that we can form an orthonormal set of these polynomials. Now, what's interesting is if you're going to insist that the Q's be polynomial, then immediately we can conclude that L is polynomial in the functions alpha, beta, and gamma. Okay? Moreover, in order for L to act on Qn but not change its degree, because L is acting on Qn. So if Qn is a second order polynomial, then Ln is going to act on it, but to satisfy this eigenvector equation, it has to return a second order polynomial over here. Okay. If you don't want to screw that up, then you have limitations on the polynomial forms of alpha, beta, and gamma. Then what we need is for alpha of x to be at most quadratic. Okay? Because you're taking the second derivative with the alpha function as a coefficient, you're reducing the power by 2, and you can restore the power by x squared. You just can't go x cubed, because then with Lx on it, it's going to have a higher power than just the original polynomial. Does that make sense? Okay. Beta x has got to be linear at best, and gamma of x has got to be a constant. Notice now alpha naught, alpha 1, alpha 2, beta naught, beta 1, gamma 0, those are all constants. I'm saying that alpha x has got to be polynomials, so these are constant coefficients in front of x squared, x1, and the number 1. Similarly for beta and gamma. Okay, so I know in the past I've left off alpha of x, beta of x, gamma of x, but now when I index them with 1, 2, and 0, those are constants. Jeez. All right? Okay, now, an interesting observation is that beta x can never be 0. Why? Can anybody look at what I've got on the board and tell me why beta x can't be 0? Any takers? If beta is 0, what is the contribution from e to the integral of 0? 1. So that means W alpha is a constant. But we need this to be 0. W alpha is a constant. These are polynomials. Do polynomials tend to go to 0 evaluated at infinity? Or no? Okay? So we actually need beta to be non-zero. Okay? All right, now. Oh, sorry, I'm going to figure out where I'm looking on my page. Yes, here it is. Okay, in fact, we need W alpha, and this is going to be our general target. We need W alpha to go to 0 faster than any polynomial blows up. We'll revisit this condition many, many times, because again, the f and the g are polynomials, and they're arbitrary, so you can take your as high power as you want, and those are obviously going to blow up at infinity. We need this thing to be 0, so we're going to need W alpha to go to 0 really, really quickly. And many of you can probably guess what function that will take, but we'll get to it in a minute. Okay, now, it turns out that there are 6 parameters that are flexible in our definition of the Sturm-Liouville system, and they are alpha naught, alpha 1, alpha 2, beta naught, beta 1, and gamma 0. Okay? Look, in case I didn't say this, Sturm-Liouville is defined as second order at the highest. Okay? And so in making sure that we don't change the overall power of the function that is the solution to it, we're requiring these for the polynomial case to at most have a quadratic, a linear, and a constant term, but that gives us 6 total coefficients which determine the system. Okay? Now, it's actually less than that because there are some things that we can do freely which don't change the story but can fix some of the values here. And we're going to use this extensively, so write down what I'm about to put. I'll write it. Oh man, this sucks. Okay, hold on. Yeah, I can do this. I can do this. I might need this integral later, so I'll let it hang out. All right. So we have condition 1, and I'll refer to these by their numbers later. L may be scaled with C1, which is a constant. So all the C's I'm going to write down are constants. I won't write down that it's a constant, but just bear in mind it's a constant. And if we scale L by C1, then that leaves the solutions unchanged in terms of the eigenvectors, but it does rescale the eigenvalues by a factor of L, or by a factor of, no, hold on. No, hold on, I wrote that down wrong. I'll have to check that. We're not going to use that, but I have to check it. So when you write that down, put a question mark next to it. X may be shifted. Well, no, that doesn't make sense because lambda going to lambda.
Isn't it like a lambda plus C1 or something?
Yeah, well, that's what I'm thinking. Yeah, I'm thinking that this should actually be C1 lambda. But don't quote me on that just a moment. But like I said, we're not going to use that. We're not going to use that part of the result. We're just going to use this freedom to do some obvious things. Okay, so this may be shifted. So X may be shifted by C2. So if we have QNX, then we can shift X by C2. And this leaves the eigenvalues unchanged. 3, we may scale X by C3. So, of course, scaling is multiplying X by the quantity C3. And again, this won't change the eigenvalues. And then 4, L may be shifted. By C4. Okay? So L plus C4 leaves the Qn unchanged. And the eigenvalues go to the eigenvalues plus C4. Okay? Now, what we're going to do is we're going to take 4, which is basically taking this L, and don't have here, here's L. And since we can just arbitrarily add a constant to L without really changing the story, we can use that to set gamma to 0. Okay? And so our form of L is going to be the quadratic and the linear terms, and we won't involve the constant. Okay? And the importance of these changes is that as long as you know what is going to change, then you can untrack this setting after you've derived all of this stuff. It's not that difficult. Okay? Now, properties 1, 2, and 3 we're going to use extensively in what follows. And what we want to do is we want to organize our analysis of Sturm-Liouville systems by basically looking at different powers in alpha. So we can start with if this is genuinely a quadratic, that is, if I'm defining my system with alpha naught not being 0. And then I'll find, some things that come from that. Then I can say, okay, suppose that alpha is linear, so alpha naught is 0, and the highest order term is going to be alpha 1x1. And then I can find some things that come out of that. And then I can say alpha is just a constant. So alpha 1 and alpha 0 are both 0. Okay. Now this is good. That sounds like a headache, but it's just a way of organizing, finding these expressions. And obviously doing x squared is going to have a different storyline than doing linear, which is going to have a very different storyline than doing constant. But what we're going to find evolves are Legendre polynomials, Laguerre polynomials, and Hermite polynomials, and others. Okay? So here we go. Let us start with the quadratic case. All right. Yeah, I'll just erase this because we won't use it anymore. Okay, so if we're working with the quadratic case, and this is by far going to be the longest of the three stories, all right, then we know that W alpha is C times the integral of x, or times exponential of the integral of beta over alpha dx. So this is going to be C times the exponential of the integral of beta 0 x plus beta 1 over x squared plus alpha 1 x plus alpha 2 dx. Wait a minute, is that right? Didn't I have an alpha 0 there?
Just scale it.
Huh?
Are you just scaling all the terms?
Exactly. I can use property 1 to rescale the operator so that the coefficient in front of the x squared is 1. Okay? I'm going to write that down because it reminds us that we still have properties 2 and 3 that we can use later on. Okay. Now, alpha of x, with alpha naught, alpha 1, alpha 2, I've set alpha naught equals to 1. These alphas are constants. Remember, they're the coefficients in a polynomial. They're constants, they're not functions. And they're real. Okay? Now let me ask you a question. If I take x squared plus alpha 1x plus alpha 2, and I want to find the roots of this, that is the values of x for which this polynomial is 0, am I guaranteed that those roots are real?
No.
Hell no. Okay? This is one of those places where imaginary or complex quantities can sneak into the story, even though you start out with completely real quantities. Okay? I mean, just imagine that guy. Okay? So, it turns out that the first thing we can do is we can consider if the roots of this were complex. And by complex, I mean they have a non-zero imaginary part. Real numbers are complex numbers, obviously. Real numbers are complex where the imaginary part is 0. But I'm going to start with a look at complex roots, which are necessarily part imaginary. And what we're going to do is we're going to rule out that those can be a part of the story. Okay? So here we go. For complex roots, what we can say is alpha x can be written in the form of x minus k star. And then W alpha is equal to C times alpha x beta naught over 2 times the exponential of a ton of junk, which is written in my notes, but I will not copy it on the board. Technically in my notes I call it stuff, but anyway, okay? Now, here's an important observation. Since alpha of x is a polynomial, and we need this to be 0, if alpha x is a polynomial, this is a polynomial raised to a power. Okay? Still a polynomial. Well, it could be a root if beta naught was 1, but nonetheless, it's not going to be anything more extravagant. It's not going to transition this into an exponential or something. Okay? So, is there any sense in which this thing is going to be the part of this that goes to 0? Because remember, f and g's, yeah. Okay? All right? Yeah.
Is the alpha on the left-hand side the same as the alpha on the right?
Yes.
Okay.
Yeah. Okay. Yeah. So wait a minute. Hold on. Is this thing ever 0 for any value of x?
Well, we said the roots are complex.
So let's do this inside. Well, yeah. So the roots are complex. So if I'm only considering real values of x,
Then yeah, it's not going to be 0.
then alpha is never going to be 0. Okay?
What about x equals 0? Unless that's a root, it shouldn't make a difference.
Right.
Oh, because of the k terms?
Yeah. Okay.
What's about the second k? X minus k, so star.
This is just a way that you can rewrite this guy in terms of I mean, look, you have 2 degrees of freedom here, you have 2 degrees of freedom here, you have the real part and the imaginary part of k. You're just encapsulating those degrees of freedom in the complex and real parts of k. Okay? All right, so if alpha w is never 0, of course an exponential is never 0, okay? So what that means is that we can't take this and adjoin it to a region which is 0. So we might have if we had a W alpha which was doing this. Sorry, let me do this. Where it's touching the axis at certain points. Then we can always take this as our definition of W alpha and then use the boxcar method to eliminate the rest of this. But the thing is if W alpha never touches 0, then you can't do that. Okay? So the complex case won't work. Now we can ask about the real case. And the real case will work with a little bit of massaging. So for real roots, what we can do is we can do the following. So for real roots, we can, first of all, reduce alpha of x. That's this expression here where alpha naught is 1. We can reduce alpha of x down to 1 minus x squared. Okay? We can do that by employing 1, 2, and 3. And I've got it written up in my notes, so I'm not going to go through it, but it's pretty obvious. Okay? But you're basically going to use these redefinitions to clean up alpha 1 and alpha 2 into given numbers. Okay? And then we're going to rewrite beta 1 in terms of 2 unknowns, q minus p, and beta 0 in terms of 2 unknowns minus p plus q plus 2. Okay? And this is going to give us a very clean story. Obviously, beta 1 and beta 0 are unknowns, and then so are qp, so you could solve those for qp in terms of beta 1 and beta 0. So this is just a redefinition. This one we're getting by applying these redefinitions, 1, 2, and 3. And again, that's written up in the notes. I just don't want to run out of time. Okay, so in this case, the ratio of beta over alpha ends up being minus p plus q plus 2 plus q minus p, times x, over 1 minus x squared. Okay? And now you can see the reason why we did this. It breaks up nicely as such. And then if we take this and we evaluate the integral that goes in the definition of W alpha, then we have okay? There's a little bit of massaging to get here. It's one-liner, but I'm not going to write it down. Then this tells us that our weight function has the form c1 plus x q to the q times 1 minus x to the p. So what we're doing is we're starting out with a quadratic operator, okay? And we are finding the weight function, or the form of the weight function that is associated with that quadratic assumption. Okay? Now there's still freedom here in choosing these values of p and q. All right? But here's the first and foremost problem. Is the weight times alpha, well, what form is this? Is this a polynomial? Yeah. So is it going to go to 0? Plus, yeah, no. It's the same problem we ran into in the complex case. These are definitely not going to vanish. This won't vanish. So it looks like we're going down the road of the complex root case, except for the following parachute. Yes?
Is it weird that we turn an exponential into a polynomial? Like c times an exponential equals c times not an exponential?
No, I did the integral of this.
Oh, okay.
Yeah, I mean, there's some steps that are skipped here. If you really want to see them, I can put them in the homework.
I don't do the homework. I'm audited.
Okay.
Awesome.
Yeah, I mean, I filled in a few steps here. I'm just not writing them on the board. But yeah, we're just integrating these things.
Okay.
So, I mean, if you integrate this, then you get, among other things, ln of this, but you're exponentiating the ln of this.
Right. Never mind.
Okay.
Talked about using the box plot. We have real roots now. Why can't we just use the box plot?
Exactly. Well, we have real roots now. That's the important observation. Remember, in the complex case, there were no real positions of x for which W alpha vanished, but in the real case, with real roots, there are places where W alpha vanish, and so we can use the boxcar or the Heaviside or whatever. Okay? So that's what we'll do. So first of all, where are the roots? What values of x does this thing vanish for? Yeah, x equals plus or minus 1. Okay? So that means that we can use the boxcar from 1 to minus 1, where we capture the non-zero value of w, and then we make it 0 outside of that, and that easily satisfies this requirement. Okay? Now, you know, here, the roots being plus or minus 1 might make you think that's the only option, you know, that you're going to end up with functions defined or polynomials defined on an interval from minus 1 to 1. Which kind of makes you sad, right? Because you love your A's and your B's and your C's. Now, I mean, why can't you just do a more general interval AB instead of minus 1 to 1? Well, what part of this story do you think you'd have to change in order to redefine the interval to be AB? Yes?
Well, we use steps 1, 2, and 3 to redefine our A as 1 minus x.
Exactly, exactly. So this is something you're going to get to do in your homework. Except for you don't have to. Okay, all right. No, yeah, you can generally make the interval anything you want. We're just making a really crisp, clean story. Okay, so, yeah, I'll just erase the quadratic part of the story and we'll summarize the results. Here we go. So we have that on the interval from minus 1 to 1, with the weight function given by 1 plus x, q, 1 minus xp, this will satisfy the defining properties of a Sturm-Liouville system whose solutions are the Jacobi polynomials. Labeled by JnPQ of x, where PQ are just the integers that you're using to define the weight product. Okay? And then n is, of course, the maximum power encountered in the polynomial. So again, so the way that you do this is you pick values of p and q. 2 and 3, 4 and 6, 11 and 12. Whatever the hell you want, once you've picked them, you've defined the weight in the inner product. You've already got the interval, so that is in and of itself the definition of a system of polynomials which span that space. Okay? So we're not just taking arbitrary values of p and q and mixing them. No. We're just picking a value of p, a value of q, that defines the system, and then we find all the polynomials within that choice. Okay? Here are some important examples. If p is equal to q, and we just call them both m, with m greater than 1, then the weight function is 1 minus x squared to the m. Okay? And these are called the Eigenvalue polys with the notation gmx is jmmnx.
Is that guy German?
He's Icelandic.
Oh, okay.
No, my favorites are Icelandic people, so I'm just going to call them Icelandic for the hell of it.
That's fine.
So that's case 1. Special case 2, I mean, obviously you can pick any p and q that you want, but these are just special cases with special names and special properties. If I pick p and q equal to minus 1/2, then my weight function is obviously 1 minus x squared to the minus 1/2. And this gives us what are called, probably the best name of all, which actually, according to the book, I can spell any way that I want, because there's so many different spellings of Chebyshev.
God. Why? Did you just decide that's how you wanted to spell it, or did you actually take that from somewhere?
I think I took it from the book.
Okay, cool.
This gives us the Chebyshev polynomials, which are, of course, Tnx is just the Jacobi polynomials with the choice p and q equals minus 1/2 and minus 1/2. Okay? But perhaps the most important example is if p is equal to q is equal to
0.
Okay,
What do I
who
put?
says 0? Raise your left hand.
I mean,
Who
it's
says
not-
1? Raise your right hand.
No, boo, come on,
All
1.
right, no, it's 0.
Yes.
What is the weight function?
1.
What polynomials are these?
The Legendres.
They're the Legendres. Okay, these are just the 0, 0 version of the Jacobi polynomials. All right? So the Jacobi polynomials in special cases give rise to Chebyshev, Legendre, and the Eigenbauer. All right? Now, fortunately, the linear and the constant stories are going to go much more quickly, but that is what we have left. We've just finished the quadratic story. Now we're going to do the linear story and then the constant story, and then we'll get the hell out of here and go home and see what's happening in the world. I know. Okay, so here we go. And these stories are going to be quite different than that one, okay? Yeah, okay. So, in the linear case, what we can first of all say is alpha x is equal to x plus alpha 2, because again we can use property 1 to make alpha 1 equal to 1. Alpha 0 is 0, because we're doing linear. We can use property 1 to make alpha 1 equals 1. But then, oh hell man, we can use 2 to set alpha 2 equals 0. So in all honesty, applying properties alpha 1 and 1 and 2, we can get alpha x to equal x. All right? Does this have a root?
Sure, short. 0.
Yeah. Okay, so we know that we can utilize the root. Let's figure out what W alpha is. In this case, we're doing c times the exponential of the integral of beta 0x plus beta 1 over x dx. This gives us cx to the beta 1 e to the beta 0x. All right, now, if beta 1 is less than 0, then W alpha goes to 0 fast enough to beat the growth in F and G. Remember, this is what we need to vanish when we go to minus infinity or plus infinity. Oh, sorry. As x goes to plus infinity. What about as x goes to negative infinity?
It's the opposite.
The opposite.
Yeah. Or less the opposite.
So we have that W alpha is going to 0 fast enough for the positive x-axis, but it's getting huge for the negative x-axis.
Chop it up.
it has a root at x equals 0, so what can we use?
The step function.
The Heaviside function, okay? So we can use the Heaviside function to make this thing what we need. And then in the end, we can use C3 to set beta 0 equal to -1. And then we can call, now remember, beta can't be 0. So we can set beta 0 equal to -1 with C3, and then we can call beta 1 s plus 1 with s greater than -1. Then Wx takes the form of x to the s e to the minus x over the interval 0 to infinity. If s is equal to 0, and again, this is just like the p and the q that define the Jacobi polynomials. You pick a p and q, and then you work everything out from there. So we pick a value of s, and then we work everything out from there. If we pick s equals 0, what are these?
What's qs?
If s is 0, we're working with this interval, and then we're working with the weight function of e to the minus x. There's a Laguerre. Yeah. Which we just called ln of x, but now we realize that that is ln with s equals 0 of x. If s is not equal to 0, then these are the associated Laguerre polynomials. Okay? All right, I'll make one more observation and then we'll go ahead and quit and I'll finish up next time. Now we have the case where alpha is constant. If alpha is constant, then we can use C1 to turn alpha 2 into 1. Remember, alpha 0, alpha 1 are both 0, so we have alpha 2, we can set it equal to 1. Then our alpha x function is just 1. W alpha ends up giving me, and this is just after writing the integral out and then doing a clever rewrite, exponential minus beta 1 squared over 2 beta 0 c exponent of beta naught over 2 times x plus beta 1 over beta naught squared. Okay? And then what we find is that if beta naught is less than 0, then W alpha equals W falls exponentially fast as the magnitude of x goes to infinity. So this actually works whether x goes to positive or negative infinity. What's our interval going to be? Negative infinity to infinity. What are the solutions in this case? The Hermite polynomials. Okay. Now what's interesting, this is a complete story. There are no more orthogonal sets of polynomials that you can find in the space up to, with a differential operator, up to degree 2. This is it. And of course, you can go to a third order and completely undo that, but
So,
yeah.
does that mean there are polynomials that don't work as well? Or did we just describe everything?
We just described everything. I mean, we're defining the system in terms of an operator of second order. Okay, if you define it of a higher order operator, this story is completely, yeah. I mean, you can imagine, I mean, this is a simple second order operator. We did the first order operator and the constant operator as well. That was where we ended up. But you can imagine how incredibly heinous this would be if we went cubic. Or third order. Yeah. Okay, so you might be bothered because you're like, where are the Fourier series? That's next time. Okay?
That's definitely what I was just thinking.
Yeah.
I was thinking, oh, I haven't had